Okay, so we continue with the sequential logic design. So we will discuss about flip-flop. So we have here the flip-flop. Next we will discuss about T flip-flop, and the next one is a JK flip-flop. So flip-flops are edge-sensitive storage elements. So the action of data storage is synchronized to either the rising or falling edge of a signal. So which is commonly referred to as a clock signal. So the value of data that is stored depends on the data present at the data input or data input D. So when the clock makes a transition at its active, so maybe active rising or active falling edge. So at all other times, so the value and transitions of the data are ignored. So there are various kinds of flip-flops, so depending on the actions of additional input signals, so that controls the storage of data. So like the flip-flop, so we're going to again modify this circuit. So essentially this is the block diagram for our D flip-flop. So we have here the input D. This is our clock. So this is your Q, state Q, and it's Q naught. So for D flip-flop, so we have here the input clock, input D. So we can find the state Q. So for clock is equals to 0. Then input X, let's say 0, or input D, let's say 0 or 1, and that gives us same state Q. If the clock is 1 or active 1, so input is 0 or data input is 0, so that gives us 0. So for clock equals to 1, that is, the input is 1 for T. So our data is Q is also equals to 1. So for D flip-flop, so we can get the characteristic equation. So the characteristic equation as, let's say for Q D, so we can take the next state Q flat. So suppose we have here 0, 1, 0, 1. Then for state Q is 0, 0, 1, 1. So our next state Q is still our input D. So that is 0, 1, 0, 1. Or that is Q plus is equals to D. So this is our characteristic equation, and that will be used in our Verilog HDL. So let's proceed to our T flip-flop. So for T flip-flop, so we designed it using D flip-flop. Then we are just added some components, so like this circuit, to generate our T flip-flop. So we have this symbol for T. So this is your clock input T. So your Q and Q naught. So the excitation table for T flip-flop. that we have our so for T flip-flop, so we have T input and our state Q. Suppose our input is 0, the output Q is still Q. Then if our input T is 1, and that gives us its complement. So the excitation table for T flip-flop, so we have our present state. By the way, so let's first generate or get the excitation or characteristic equation. So the characteristic equation for T flip-flop is that we have, let's say, our input Q, T. So to get our next state Q plus, we have your 0, 1, 0, 1. Suppose you have input 0, 0. Our next state is 0. This is 1, 1. This is 0. So that means our Q plus, our characteristic equation is T Q prime or Q bar plus E bar Q. So this is just a XOR gate for our flip-flop. So the characteristic equation is derived using K-map. So we can able to perform K-mapping for this one. So also let us take the excitation table so that we can use it in our sequential logic design. So suppose our present state is Q, the next state is Q plus, then I'm sorry. Okay. So we are to get the output T or input T for that circuit. Suppose our present state 0, 0, 0, 1, 1, 0, and 1, 1. So the output T is still 0, 1, 1, 0. So for, so remember this table, our excitation table. Then for, let's go back to D flip-flop. So the excitation table for D flip-flops, that we have our present state Q, Q plus, then we have D. So to get the input for our D flip-flop, so we have 0, 0, 0, 1, 1, 0, 1, 1 input. And that means from this equation, so we all know that Q plus is equals to D, so that means this is 0, 1, 0, 1. So again, we will use this excitation table to design a sequential logic circuit. So let's move now to JK flip-flop. So for JK flip-flop, so we just again modify this circuit so that we interconnect. So instead of connecting this one to Q, so we connect it with its complement. And then we arrive with this circuit for JK flip-flop. So for JK flip-flop, so we have input J, K, then our state Q. So for input 0, 0, so we have our present state Q. For input J0, K is 1, so we have here 0. J is 1, K is 0, so this is 1. And 1, 1, that gives us Q complement. So the block diagram for our JK flip-flop. So we have here JK input and the output. So we have the Q not state. So for the excitation table for our JK, so we can derive that using the state Q, then the input JK. So 0, 1, 0, 1. So our Q plus, our next state Q. So this gives us, so according to this table, so we have here 0. 0, 1 gives us 0. So 1, 0, 1, 0. So this gives us 1, 1, 1, 0, 1, 0. So we can perform K-map for this one. Then our characteristic equation for JK is that we have J Q bar plus K bar Q. This is our characteristic equation. So we can use that to generate or get our next state. So the excitation table for JK, so we have our present state Q, next state Q plus, then the input for our JK flip-flop. So suppose we have here 0, 0, 0, 1, 1, 0, 1, 1 input. So JK is 0 for K. That is 1 or 0, or we can write X. So that means don't care, it's either 1 or 0. So this one X, this is X1, X0. So again, we will use this table or excitation table to design our circuit. So for the next video, so we will perform a sequential logic design using Verilog.